I want to talk about the structures and conformations of simple alkanes using Newman projections. And we're going to start with a very simple alkane, which is ethane. I've drawn it here in what is sometimes called the sawhorse projection. And what we're going to do is we're going to think about converting this to a Newman projection. And we're going to make a Newman projection along this bond right here, with this carbon right here is in the front, this one is in the back, and I've color-coded things here. So my hydrogens in the front are these: red, gold, and green. I've numbered them 1, 2, and 3. In the back I've used letters A, B, and C, and you can see they're also color-coded. If we look at this three-dimensional model, what we're going to be doing is we're going to take it and we're going to rotate it. This is the same conformation as this here. And I'm going to rotate it so that one of the carbons completely blocks out the other carbon. And I'm going to turn it a little bit so you can still see that the other carbon is there. But that's how we're going to start off our Newman projection, with the two carbons in a line. And you can see that all of our groups in this original conformation that I've started with are lined up. This is what's sometimes called the eclipsed conformation. And if we look at the Newman projection for that, what you can see is the atoms that are in the front go all the way to the middle of my sphere. The ones in the back only touch the outside. And I can't draw them right in front of one another because then I wouldn't be able to see what I was looking at. But this is meant to represent that these are overlapping with one another, just like I have in this conformation. The green is in front of the blue, the red is in front of the purplish pink color, and the yellow or gold is in front of the orangish color. Now what I'm going to do is I'm going to take the group in the front and I'm going to rotate it counterclockwise, so in this direction, so that the green hydrogen is halfway in between this blue and this purplish hydrogen. And I'm going to do that on my three-dimensional model first. I'm actually going to have to slide this over a little bit. So let me try to do that now. Oops, that's the wrong way. That's clockwise. And that's counterclockwise. So I want it right about there. And if we look at what that looks like now, the green is between the blue and the purple. We can look at the same thing in our Newman projections over here. And our Newman projection would look like this, with the green and gold, green, gold, red, red, purple, orange, blue, purple, orange, blue. And if I started at 0 degrees, this would be rotating the front group by 60 degrees. Well, I can rotate it another 60 degrees. For a total of 120 degrees and get something like this. You can see I went from eclipsed to staggered to eclipsed again. If I do this rotation on my three-dimensional model, I get some, oops, I'm going the wrong way again. I need to go counterclockwise, and I get something like that, where the green eclipses the purple, yellow, blue, and red eclipses the orange. Finally, I can do one more 60-degree rotation for a total of 180 degrees. And when I do that, again, I get a staggered conformation. And if I do that on my three-dimensional model, what I get is something like this, where now the blue and the green are anti to one another. The yellow and the orange are anti. The purple and the red are anti to one another. Let's talk a little bit about the energy of these conformations. And what you have probably discussed before is that the eclipsed is higher in energy than the staggered. And that's because of the close approach of these hydrogens in the eclipsed compared to the staggered. What I want you to notice for the simple molecule ethane is that all of the staggered are the same in energy and all of the eclipsed are the same in energy. And we can actually look at a plot of this using a slightly different program. This is another program for displaying molecules in 3D. And what I can ask this program to do is to calculate the energy as it rotates these hydrogens around this bond. So let me do that. It rotates it and it calculates it. I don't need this box right here. But what you can see is at 0, where the groups are eclipsed, that's my high in energy. Every time I go to staggered, it gets lower in energy. I can actually click on here, the low energy, it puts it in the staggered conformation. I can rotate this so you can see that that's staggered. If I go to one of the high energy conformations, you can see it's eclipsed. This is staggered, eclipsed, and in the between is somewhere in between. I want to look at how things would be different if we change from ethane to butane. So I've changed everything in these diagrams to butane. We're going to be doing a Newman projection using C2 and C3 as our two carbons. And qualitatively, in these pictures, not much changes. All I've done is I've gone through and everywhere where I had an H that was green and an H that was blue, I've changed it to a CH3. So I put two CH3s here, changed these to CH3s. Everywhere where I had a blue or a green hydrogen, I changed it to a CH3. Doesn't look qualitatively very different, but it actually is different because there's a difference between having CH3s near one another and having a hydrogen near a CH3. CH3 takes up more space, hydrogen takes up less space, so it's going to be energetically higher in energy when my CH3s come close together. We can see that better on our three-dimensional model, which I have here. What I've done is instead of putting in an actual CH3 in the green and a CH3 in the blue, just to keep things simpler and easier to visualize, I've made a larger sphere that is green and a larger sphere that's blue to represent my larger CH3 groups. And if I line these up the way we have them, that's how we're starting. And I can rotate around the bond like I did before. And what I want you to notice is that when I have these two larger spheres near one another, that's going to be higher in energy than when I have them further away from one another. Try to get it just right. So even though this is staggered and this is staggered, in this staggered conformation, these two large groups are near one another. That's called a gauche interaction. In the other staggered conformation, the two largest groups are far enough away from one another that I have a lower energy structure. And we can actually see that if we go and plot the energies of these conformations. So this is our butane in the eclipsed conformation with the two methyl groups eclipsing one another, and I can tell it to select this group, this group, this group, and this group, and calculate the rotational energy as we go around there. And what you can see is that the conformation where the two methyl groups are eclipsed, and I want to rotate this like this, is much higher than the other eclipsed conformation where it's the hydrogen eclipsing a methyl group. And this staggered conformation where the two methyl groups are close together is higher in energy than the staggered conformation where the two methyl groups are anti to one another. And we can click, like I said, anywhere here. This is the eclipse conformation where the hydrogen and the methyl are eclipsing. This again is the high energy one where the two methyls are eclipsing. And finally, the lowest energy, the methyl groups are anti to one another.